Okay, so now that you know you can program your FPGA, let's talk about the software part or CAD. So I want to talk about now about computer-aided design that make it easy, basically makes it easy to implement the logic circuit by using a programmable logic device. So there is a flow to that. Okay, there's a flow for computer-aided design. A typical FPGA CAD, if I talk about FPGA, has a flow that I'm going to cover now. So the flow would be first you have your design entry. So first one is design entry. Okay, so what is design entry? First you have to, when you start, you say, okay, I want to make this, for example, a circuit. So for FPGA CAD, you can do it either by a schematic diagram or by using a hardware description language like VHDL and Verilog. So VHDL and Verilog, the code is one way. The other way is that you can just draw the schematic. You can say, okay, I want this going to that, going to that. And then, let me see if I have it in Quartus. And then you can, that's the first part, okay? So you either have to code it, you have to either code it with Verilog or VHDL, or you can you can use a schematic diagram. That will be the first step, design entry. After that, you go to synthesis. So the enter design is now it's synthesized into a circuit, right? Yes. No, no, you can't do that. Just from the truth table, no, no. You have like a talent for simplifying things, even for I mean, you have good ideas, but they don't have that. No. Uh, yeah. So you can either code it like something like this. If I bring it to the exactly, yes. So yes. No, but you have good ideas. Even for the eagle, it was a good idea. Why doesn't it do it for us? But it doesn't. So you have to code it. You know, it's I'll show you like with Verilog, you have to either code it like this, or you have to draw the I don't know if I have yes, draw the logic gate. So I have open project. I can show you if I have light. Yeah, I don't know where is it. But yeah, you either can, it's like coded like this. So it's very, I'll show you what these means. Or you have to draw it. Yes, no truth table, no. And then, so these are two ways of doing it. And then you go to synthesis. That's basically the enter design is synthesized into a circuit that consists of, as I told you, logic elements and blocks and cells. So that's the next step. There is a flow, as I said. Then The next step will be functional simulation. So functional simulation is the circuit that you have just synthesized is getting tested to verify its functional correctness. But it doesn't take any, it doesn't check any timing issues. It's just its functionality is checked after you synthesize your circuit. Okay, so that's the next step. And then, so as long as your circuit is functional, then you can go to the next step, which is fitting. I mean, the software goes. Yes, yes, exactly. So your gates are in a way that it's working. It gives you an output, right? So for input, it checks to see if it functions. So for inputs, it gives off output. Then it goes to fitting. Fitting, as the name says, it just chooses the routing wires in the chip. So it will, because you have logic cells, as I said, right? So it will choose the best paths, the best routings that can create the circuit that you just design. So that's the fitting part. So it determines the placement of the logic elements that you have, chooses the routing wires in the chip to make the connections between a specific logic elements in FPGA. That's the fitting part. Then you go to, that's what it does. So that's a CAD flow, as I said. Then it goes to timing analysis. So what do I mean by timing analysis? Timing is an important subject that you might not have taught when you were learning about logic gates. So a very simple logic gate, you have learned, okay, I have an OR going to an AND, and if I give you the inputs, you give me the output, right? So that's how you learn. But in reality, it matters the distances and the length of your wires, because by the time, for example, if you have a long wire going and then a short one with another logic circuit, the output actually might get messed up, because by the time that this information gets here, maybe there is another information here, so your output wouldn't be accurate. So timing analysis, that's called propagation delays. Maybe the propagation delays here and here should be in a way that you get always the right output. Otherwise, you might get wrong answers. So that's where timing analysis will come to life. Propagation delays along these paths are analyzed basically to provide to provide an indication of the expected performance of your circuit. Is it clear? Okay. So this is a very important concept in digital design, that you have to always consider the propagation delays. Okay, so after fitting, because now it makes sense, because in fitting, it chooses the routes and the cells, then it checks the timing analysis, and then after that, we have timing simulation. So, yeah. Yes, yes, yeah, yes. Good point. So going back, it's more like this if you look at it. So you have design entry, then it will go to synthesis, then it will go to functional simulation. So here, for example, in functional simulation, if it doesn't work, if the design is incorrect, it will go back to design and it gives an error. Then if it's okay, very good question. So then if it's okay, then it will go to the next step, which is fitting, right? Then it goes to fitting, it does it itself. Then it will go to timing analysis. And here checks again. It checks again. And so it's an if here, which is in flow looks like this. Here, it asks itself, is the timing requirement for the circuit is met? If it's no, then it goes back to either fitting, and if it can't figure it out, then it goes to design entry. Okay. So as you said, it checks it. And then go to the next step, which is programming and configuration, which is the timing simulation. So in timing simulation, now you have a fitted circuit and it's tested again to verify both the functional correctness and timing. Okay. And again, if it's good, it's good. If it's not, it will go back. And then the last step is programming and configuration. So that's when the design circuit is implemented into a physical FPGA chip in the last step. So it doesn't go and do it right away. It follows all these flows that I talked about. And then the design circuit at last is implemented in a physical FPGA chip. And that's by programming the switches and configuring the logic elements inside the cells and blocks and establish the required wiring connections. Okay, so that's the CAD flow. Now,